Welcome back to the deep dive. If you follow the world of artificial intelligence, you probably know that for all the amazing things large language models can do, there's this one challenge that just consistently trips them up. It's the abstract reasoning corpus, or ARC-AGI benchmark.
Yeah, people often call it the IQ test for AI. And well, the reason it's such a big deal, such a critical benchmark, is the huge difference in performance. You see, a human can look at these abstract pattern puzzles and solve them with what, about 85% accuracy?
All right, pretty good.
But until very, very recently, the best LLMs out there, the ones writing emails, generating code, they were stuck. Really stuck, around maybe 18% accuracy.
Wow, 18 versus 85. That gap really says something, doesn't it? It gets right to the heart of the generalization problem.
Exactly. LLMs are fantastic at processing information they've seen during training, mountains of it. But ask them to figure out a new rule, something they haven't explicitly encountered.
They just fall apart.
They do. They might be able to summarize the entire web. But figuring out a seemingly simple pattern puzzle, like why a little 2x2 red square should suddenly become a 3x3 blue one, based on a couple of examples, that's tough for them.
So that huge difference, that 67-point gap, that's kind of the frontier, right, between the pattern matching we have now and maybe, real AGI.
That's a great way to put it. It really highlights the boundary.
Okay, but the reason we're diving into this today is because our sources are talking about a really unexpected leap forward. A genuine breakthrough. We're looking at work by researcher Jeremy Berman, who used the Sonnet 3.5 model and managed to push the state-of-the-art score on the public ARC leaderboard from, 43%?
Yeah, the previous best was around 43%.
All the way up to 53.6%. That's a big jump.
It's a massive jump. And what's really fascinating, I think, is how it happened. It wasn't just throwing more data at it or building a fundamentally bigger model. No, this performance boost came from a totally different approach applied after training, at test time. They're calling it Evolutionary Test-time Compute.
Evolutionary Test-time Compute. Okay.
And we really need to unpack what that means, because it could be, well, either a very clever engineering solution, sort of hack, or maybe it's a genuine step towards AI reasoning differently.
All right, let's do that. Let's unpack it. For anyone maybe less familiar, can we just quickly recap what ARC-AGI actually asks the AI to do?
Sure. So ARC-AGI is all about abstract pattern recognition. You or the AI get shown maybe 2 or 3 examples. Each example is a pair, an input grid and an output grid, little pixel grids.
Okay.
And the task, the real challenge, is to figure out the single hidden rule that transforms that input grid into that output grid, just from those few examples. Then, once you think you've got the rule, you have to apply it to a new input grid, one you haven't seen, to predict the correct output.
Got it. So it's not about knowing tons of rules beforehand. It's about inferring the specific rule from almost no information.
Exactly. Minimal context. And that's why it trips up LLMs.
Because they haven't seen that exact rule before.
Precisely. The core difficulty is identifying novel conceptual patterns. If the model saw thousands of examples, like turn the corner blocks from red to blue, it would probably get it right. But if the rule is something weird, like reflect the main shape along its longest diagonal, and then fill the outer border with the color that comes next alphabetically.
Something it's never encountered.
Right. Something truly novel, it fails. So this leap to over 53%, it kind of validates the core idea behind this new method. The idea is that maybe these big frontier models do have the necessary intelligence, or something close to it, hidden away. But you need to, poke and prod them in a very clever, iterative way to get the right reasoning out.
Okay, and that poking and prodding, that iterative process, that's the evolutionary engine part. It's inspired by genetics.
That's it, exactly. It's inspired by genetic algorithms, by natural selection. The fundamental shift is this. Stop trying to make the LLM directly output the final grid.
Okay, so what does it output instead?
Instead, the goal is to evolve a piece of Python code. A specific function, a little program whose job is to take the input grid and transform it into the output grid.
Ah, so you evolve functions, not pictures. Why functions?
Because you can run them, you can execute the code, and check if it works against those few examples you're given. It's verifiable.
Makes sense. Okay, so walk me through it. How does one generation of this evolution work?
Right, so it starts with the initial generation. You prompt the LLM, maybe Sonnet 3.5 in this case, to write, let's say, 50 different Python functions. Each one is an attempt to solve the same ARC puzzle.
50 different guesses coded up.
Exactly, and immediately you test them. You run each of those 50 functions against the example input-output pairs provided in the puzzle. That's the fitness evaluation step.
Using those few examples as like a temporary training set just for this evolution process.
Precisely. And the scoring here is really important, quite nuanced, actually. They use two tiers. The primary score is simple. How many of the example grids did the function solve perfectly? 0, 1, 2, or maybe all three.
Okay.
But there's also a secondary score. This one counts how many individual cells in the output grid the function got right, even if the whole grid wasn't perfect.
Ah, so you don't throw away functions that are partially correct.
You definitely don't. That secondary score is crucial for keeping potentially useful bits of logic around, even if the whole function isn't quite there yet.
Clever. Okay, so they're scored, ranked, then what? Survival of the fittest.
Pretty much. The best performing functions based on those scores are selected as parents for the next generation.
And how does the LLM use these parents to make better offspring functions?
So you take a top-performing parent function, you note its score, maybe where it failed, and you feed all that back into the LLM within a carefully crafted revision prompt. You basically tell the LLM, here's a function, here's how well it did, here's where it messed up. Now write a better version.
An optimized version.
The offspring.
Exactly. And you repeat this whole cycle. Generate, evaluate, select, revise maybe 4 or 5 times, 4 or 5 generations. Each cycle, you're guiding the LLM, hopefully, closer and closer to a function that actually captures the underlying rule.
I like the analogy they use in the research. Thinking about it like exploring a huge space of possible solutions. You start out by just throwing out random guesses, like scattered red dots all over the map. Most of them miss the mark completely.
Right, those are your initial functions, mostly failures.
But then you find a few red dots that are maybe a bit closer to the target. You select those few promising ones.
Maybe the top 10, even if they're still not great.
And then for the next generation, you tell the LLM to generate new guesses, blue dots, but only in the vicinity of those promising red dots. You focus the search. Exactly. You're narrowing the search space intelligently. Then you repeat. Find the best blue dots, generate black dots clustered even tighter around them. It really mirrors how evolution works, right? It doesn't start from scratch every time. It builds on what worked before, refining successful traits. And that focused refinement seems to be key to getting up to that 53% accuracy.
So it's not just about generating lots of functions, it's about the depth of that refinement. Which brings us to that experiment they did, comparing deep versus shallow architectures.
Yes, this was a really critical finding. They compared two setups using the same amount of overall computation. One was shallow, generate a lot of functions, say 200, all in one big first generation and pick the best. The other was deep, generate fewer functions per generation, maybe 50, but do it over 4 distinct generations, refining each time.
Okay, same compute budget, different strategy. Which one won?
The deep architecture performed significantly better. It hit about 75% accuracy on their test set, compared to only 70% for the shallow one.
So spending that compute time on iterating and refining was more valuable than just making a huge number of initial guesses.
Absolutely. And the data really backed this up. They found that for the deep architecture, something like 42% of the successful solutions, the functions that finally cracked the puzzle were only discovered in generations 2, 3, or 4.
Wow. So if they'd starved after the first generation, even that big one of 200?
They would have missed almost half the solutions for the harder problems. It proves you really need that multi-step refinement process to hone in on the answer.
And this also ties into that problem you mentioned, the local maxima trap.
Exactly. Imagine your top-scoring function after generation 1 solve examples 1 and 2 perfectly, but it completely misses the point for example 3. If you only use that top function as the parent, you might just keep refining solutions that are good at examples 1 and 2, but you never crack example 3. You get stuck.
Right, because maybe some other function, ranked lower overall, was the only one that had the key insight needed for example 3.
Precisely. You need to preserve that genetic diversity, so to speak. You need insights from across the board. And the solution they implemented for this is called the pooling approach.
Pooling, okay. So instead of just using the single best parent function.
Right, you select multiple parent functions from the generation, and crucially, you make sure that your pool includes at least one function that successfully solved each of the different training examples. So if you have 3 examples, your pool must contain a function that solved example 1, one that solved example 2, and one that solved example 3, even if they weren't the absolute highest scores overall.
I see. So you gather all the essential insights from the generation.
Yes. You then combine information from all the functions in that pool into a single, more complex revision prompt for the LLM.
Okay. But doesn't that make the prompt really big and complicated? Does the LLM get confused trying to address failures from like 5 different parent functions at once?
That's a fair point. It's a potential risk. You have to manage the prompt complexity. But the benefit they found outweighs that risk. It forces the LLM to synthesize the collected wisdom of the generation. It ensures that crucial bit of logic needed for, say, example 3 isn't lost just because it came from a lower-ranked function initially. It's about ensuring genetic completeness in the prompt.
Got it. Completeness. And given the practical constraints they face in the competition, like only 12 hours of compute time and a $10,000 API budget.
Yeah, real-world limits.
They didn't just pick one method, the single parent or the pooled parent approach.
No, they hedged their bets for efficiency. The final architecture they submitted actually ran 2 tracks in parallel. Track A used the traditional single-parent evolution, good for refining solutions quickly when you have high confidence. And Track B used the pooled multi-parent evolution, better for exploring diverse solutions and avoiding those local maxima traps.
A hybrid system.
Yeah.
Smart. Using both to cover the bases and search the solution space effectively within the time and budget.
Exactly, maximizing the chances of finding a working function quickly.
Okay, but none of this complex evolutionary process works if the LLM isn't generating decent, usable Python code in the first place, right?
Yeah.
What were the tricks on the prompting side?
Yeah, the prompting was absolutely fundamental. The main technique, probably unsurprisingly, was chain of thought prompting, or COT.
Right, COT, where you make the LLM explain its reasoning step by step before it gives the final answer.
Precisely. You don't just ask for the Python code, you instruct the model. First, explain in natural language how you think the transformation works. Step 1, identify shapes. Step 2, check colors. Step 3, apply reflection. And then you ask it to write the code based on that reasoning.
And that helps because
It dramatically improves the logical coherence of the code. The LLM is forced to structure its thoughts first, making it less likely to just output random code snippets that happen to fit statistically but make no logical sense. It anchors the code in a reasoned process.
Okay, that makes sense.
What else? They also found that one-shot prompting worked best.
Meaning giving it just one example of a good solution in the prompt.
Yes, one single detailed example of a previously successful prompt reasoning code sequence. Apparently giving it 2 or 3 examples, few shot, didn't improve things, and just used up valuable context window space. One good example was the sweet spot.
Interesting. Keep it focused.
And maybe the most belt and suspenders part of the input. They fed the actual grid data to the model in 4 different formats simultaneously.
4 formats. Why? I see here. Grid dimensions, a base64 image encoding, an ASCII text representation, and a Python nested list format. Seems redundant.
It seems redundant, but it's about robustness. The idea is maybe the LLM might misinterpret the ASCII grid slightly, but it could still extract the correct pattern from the base64 image representation, or the list format.
So it gives the model multiple ways to see the data.
Exactly. It minimizes the chance that the whole attempt fails just because of a simple input parsing error. It makes sure the LLM is spending its effort on the actual reasoning part of the problem, not getting tripped up by the data format.
Okay, so that covers the how. The evolutionary engine, the architecture, the prompting. It's an impressive piece of engineering.
It really is.
But now we get to the deeper part, the philosophical part, maybe. What does this success actually tell us about AGI? Because this whole approach seems to highlight a fundamental difference between how humans solve ARC and how the LLM solved it here.
Yes. Deduction versus induction. This is really the core issue this raises.
Explain that.
Okay, so when humans tackle these ARC puzzles, we're primarily using deductive reasoning. We look at the examples, we form a hypothesis about the rule, and we check if the conclusions necessarily follow from that rule. If the rule is X and the input is Y, the output must be Z. There's a sense of logical certainty.
Right, like All men are mortal. Socrates is a man, therefore Socrates must be mortal. Guaranteed.
Exactly. That's deduction.
Yeah.
But LLMs, their entire training process is based on predicting the next token. They learn from vast amounts of data to figure out what word or piece of code is statistically likely to come next. That's inductive reasoning.
Making educated guesses based on patterns and past experience.
Educated guesses, yes. But without that guarantee of certainty, it's fundamentally probabilistic, not logical necessity.
So wait, when an LLM uses chain of thought and it outputs that step-by-step reasoning, that sounds really logical. It's not actually deducing.
Well, that's the million-dollar question, isn't it? It's doing an incredibly good impression of deduction. It's generating sequences of text that are highly probable to be logically sound because it has seen billions of examples of logically sound arguments in its training data.
It's mimicking logical structure based on pattern.
Precisely. It's pattern-matching logical discourse. And this ARC breakthrough, using this evolutionary method, it leans hard into that probabilistic nature. Generate hundreds of guesses, use the examples to figure out which guesses are better, refine the guesses.
So does this mean AGI could actually emerge from systems that only use induction? Can you get to true general intelligence just by being an amazing guesser and refiner?
Well, the research suggests maybe two possibilities here based on this ARC result. Possibility one is, yeah, maybe the mimicry just gets so good. So incredibly good at pattern matching deduction that it becomes functionally indistinguishable from the real thing.
Yeah.
Could an LLM use induction to, say, discover the theory of special relativity? Maybe.
That's a big thought. And the second possibility?
The second possibility is what this evolutionary test-time compute method embodies. Maybe you don't need an internal deduction engine if you can just generate a massive number of educated guesses, potential solutions, and then use a really smart search process like this evolutionary algorithm to find the right one. Test-time compute essentially replaces internal deduction.
Okay, generate and test.
Yeah.
But doesn't that run into a problem?
It runs into a huge problem. Let's call it the verifier problem.
Verifier problem, okay.
Look, for ARC, verifying a guess is easy. You generate a Python function, you run it on the 3 example pairs. Does it produce the correct outputs? Yes or no? Instant verification.
Right. The problem itself provides the verifier.
Exactly. But what about tasks that define true AGI? Like designing a completely novel type of fusion reactor, or proving a complex mathematical theorem, or writing a groundbreaking legal argument. How do you verify that the LLM's brilliant-sounding guess is actually logically sound, correct, or safe?
You can't just run it on 3 simple examples. There are no simple examples for truly novel, complex tasks.
Precisely. You'd need some way to confirm its logical soundness. And if you tried to build another AI to act as the verifier, well, what would that verifier need?
It would need the ability to perform genuine, guaranteed logical deduction to check the first AI's work.
Which means the verifier AI would itself need to be AGI, or possess that deductive capability we were trying to bypass in the first place.
So the verifier problem suggests this evolutionary test-time compute, while amazing for ARC, might be a specific solution for problems where verification is easy. It's not necessarily a path to general intelligence for open-ended, unverified tasks.
That's the strong implication, yes. It looks more like a really sophisticated engineering hack for bounded problems rather than the secret sauce for true AGI capable of, unguided scientific discovery.
Okay, so if pure induction, even scaled up with evolution, isn't the full answer because of verification, what kind of architecture could support genuine conceptual reasoning, the kind humans use? This brings us to that idea about training models differently, inspired by Yann LeCun's work, JPA.
Right, the joint embedding predictive architecture ideas. The core thought process here starts with how humans seem to operate. We generally think in concepts first, right? An idea forms, and then we select words to express it.
Yeah, language follows thought, mostly.
But current LLMs are trained end-to-end to optimize for token accuracy, predicting the next word, the next piece of code. It's optimizing for surface-level linguistic or code structure.
Good.
The JPA-inspired proposal flips the objective. Instead of training the model to predict the next token, you train it to predict, essentially, feature-level representations of upcoming conceptual chunks in an abstract space.
Whoa, okay, predict the idea, not the word. How does that help?
Well, the theory is, by forcing the model to optimize its predictions in this abstract conceptual feature space, rather than just the space of words or tokens, you are directly training it to understand the underlying relationships, the necessary connections between abstract concepts.
The very thing you need for deduction.
Exactly. It aligns the model's learning objective directly with the mechanics required for logical reasoning and understanding abstract structure, the skills needed for ARC, solved internally without needing potentially billions of external guesses. You're trying to optimize for coherent thought, not just coherent language.
That's a fundamentally different approach to building these models.
It is, very much so. Still highly theoretical in many ways, but it points towards a different path.
Okay, this has been a really fascinating journey, right to the cutting edge, and maybe even peering over it slightly. So the big takeaway for you listening right now seems to be this. The ARC-AGI breakthrough using this evolutionary test-time compute is genuinely impressive. It shows that clever, scaled computation, guided by evolution, can really help overcome some of the current fundamental limits of LLMs and generalization. It's an amazing engineering feat, maximizing what today's models can do.
Absolutely. But it might still be just that, an incredibly sophisticated way to work around the core limitation rather than solving it directly. It relies heavily on the fact that ARC solutions are easy to verify.
Which brings us back to that final provocative thought.
Right, the verifier problem. If ARC is hard because it requires deduction, but solvable with this evolutionary hack because verification is trivial, what about true AGI? For those boundless, complex, truly novel tasks where verification isn't easy, where you need guaranteed logical soundness before you act, what kind of new architecture, what kind of internal component would a model need to provide that guarantee?
What does a built-in verifier, based on deduction, actually look like inside an AI?
That's the question to ponder.
A deep question indeed. Thank you for taking this deep dive with us today. We'll see you next time.